Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thanks, Sue. Yes, screensaver. So yeah, I'm a systems guy. I like to build things, and I like to feel that they work. So I've really enjoyed so far and anticipate having more interesting discussions with you people here, because in some ways you're a little closer to reality than I am in the ivory tower. So a couple of years ago, I was kind of touched by spam as a user, and also I was a little bit interested in it, and I tried to convince some people that there were better ways of filtering spam, and in particular I tried to convince some open source developers, and they told me I didn't know what I was talking about. And I also had a student who wanted to do some work on spam, and I tend always to ask my students, well, how are you going to know whether you've succeeded or not? And it seemed that there wasn't really much of or at least in the way of available corpora and methodologies for finding out whether spam filters worked or not. So I got a little bit sidetracked in doing spam evaluation, and I'm very happy that very recently, actually just in the last couple of months, I've actually had an opportunity now to actually try some new things in spam filtering. So I'll talk a little bit about spam filter evaluation, and also a little bit about some of the things I've been working on. So what is spam? I won't belabor the introduction here, because we all know exactly what spam is, particularly the people in this room. But, and I think we probably all agree it's difficult to define, but at least within the TREC evaluation context, this is what we came up with, unsolicited, unwanted, indiscriminate, relationship between sender and receiver. The main thing I want to say here is that this is still a hard definition, even though it may vary from, one piece of email may be spam to one person and not spam to another. It's not just something the user doesn't want. So the user may be a very good witness and have information that's very difficult to glean about whether this is spam or not, but it's not just totally up to the user. So
the relationship doesn't necessarily mean I don't want it.
Oh, that's true. That's absolutely true.
I get invited to something where I don't want it.
And perhaps, and having no current is actually too hard a distinction as well. It should say outside of the accepted current relationship or something like that. But this was as well as we could do. Even this makes it hard enough to class. Even this makes it hard enough for even the recipient to, given these rules, to classify, a percent or whatever, and it makes it really hard for a third party to look at some rules. One of the things I did was I looked at the Enron corpus, and there are all kinds of newsletters for manipulating the stock market, or how to do betting in Antigua or whatever. And originally we thought a lot of these were spam, and later we thought, no, I think they probably were actually not spam. So here's our kind of model for spam filter, for what a spam filter is supposed to do, at least from the human perspective. It's supposed to take incoming email, classify it either typically into two baskets, maybe into three, but I think this is basically covers it off. And one is just your normal mailbox. So you process your mail. You don't want to see spam, but if you do see spam, you identify it as such, and maybe you tell the spam filter about it if you're feeling nice. This is a completely different user interaction. If the spam filter is implemented as the bit bucket, then the user interaction is not much at all. If you actually do save the stuff, you probably want to do various searches on this. Rather, you don't think of this as something that you're going to be stepping through in the same way as your normal incoming email. It's something that you may have to search for various reasons. So you might want to rank it according to how certain you are that it's spam, or you might want to rank it according to what the perceived risk or cost of losing this mail might be, or you might find that something has gone missing, and then you want to say, just before I do this all the time. As Sue said, I have I do programming contest stuff that's international, so I get large zip files from people in Bangladesh, that are sent through chains of compromised servers that are real mail, and they have a great deal of trouble, getting through spam filters. But when my correspondent says, "I just sent you 5 messages with attachments, you better go check your quarantine file," then at least I want to be able to search it. But I just want to make the point from the human interface point of view, these are different things, and it still can be, a lot of people say, "Why use a spam filter? Because I don't trust the spam filter, and I'm going to look at every piece of email anyway." Well, even if you're planning, sorry?
They're not getting enough.
They're lying, but I think you can prove that they'll actually do a worse job than them plus the filter, but that's another issue. But you can also, from a human interaction point of view, saying even if you really want to do that, you still want to treat these as 2 different tasks: the stuff that you expect to be email and process as email, and the stuff that you expect to be spam, and you want to try to search to find all of the legitimate email in this haystack of spam. Anyway, so some or all of this might be fed back, and there's actually a bit of a missing diagram here. I should have an arrow coming in from the outside world, because this filter may, of course, be collaborative, or it may use other kinds of external resources. In the context of Trek is very much built on this closed laboratory repeatable experiment thing, so for Trek we didn't use any outside resources. And of course, if the filter is going to give a different result every time you run it and maybe modify its environment, it becomes orders of magnitude more difficult to test. I mean, I'm not saying you shouldn't test, but that's logistically a much bigger effort. So this is the basic thing, and essentially we wanted a test that modeled this as well as we could. And so for Trek, we just finished a spam filter. Yes?
It's like a personalized spam.
Not necessarily. This diagram is abstract enough that this can all be server side. And as I say, if you have this arrow for shared resources, the shared resources can be other ones that reside on the same server. Within the Trek context, we originally said the incoming email is 1 person, but in fact for the Enron email, it's actually 150 people all mixed together. So one could think of this as the Enron executive mail server deployment. It really doesn't change any of these things, other than it might change the frequency and delay with which users might report back these misclassification errors. They might not report them back at all. So Trek likes to test things, and they have these various tracks that have different applications. And so for 2005, we had a Trek a spam evaluation track, and that involved, we gathered 4 corpora of email. We presented them to the filter in chronological order. The filter had to implement a command line interface that basically would take 1 message at a time, do a soft classification on it, that is, give a score, as well as a hard classification, hammer spam. And we did run this with this ideal user that knew exactly the right answer and communicated the right answer back to the filter immediately after doing the classification. So this probably works to the filter's advantage, but for next year we're looking at ways of maybe modeling delay and error and things like that and user feedback, but we wanted at least a baseline to start with. The competition, at least in terms of publicly available corpora and methods, is pretty sparse. There's a spam assassin corpus, which I should have put on this list, but I neglected. It was used as a pilot corpus for Trek, and in fact, all the results I'm going to show basically the same thing on the spam assassin corpus. So we had these 4 sets of email. Only the set we built from the Enron email was made public. So it was sent to the participants where they ran their spam filter. For the other 3, they had to implement this command line interface and send us their software. And I ran 1 of the corpora, and I outsourced running 2 of the other ones. So we had 4 independent sources of data that we ran things on. And then, well, I'll get into evaluation measures later. The previously existing literature, for the most part, uses these two public corpora. Link spam is mailing list data with a bunch of spam added to it. And then it's all stripped of special characters and reduced to lowercase, and all the header information is stripped and all that kind of stuff. So it actually tends to be a very easy corpus, notwithstanding the fact that a lot of the structure and funny marks that are typically associated with spam are absent. Evaluated with very typical supervised learning methodology. You've got this static set of mail. You assume it's not a sequence but a set, and that it's uniform, or it's randomly drawn from some uniform population. So you split it up, 10 different ways into 90% and 10%, and train on the 90% and test on the 10%, and then sum all the scores together.
Do you really not have date for that?
There's date?
Yeah, date for mail spam?
No, link spam that's been stripped. There's no header information at all. PU1 it uses very much the link spam model. It's real email though, except to preserve privacy. After it's stripped of punctuation and all that kind of stuff, every unique alphanumeric string is then translated into some number arbitrarily, so that all you have is this list of features. They're still in the order present in the original, but the lexical characteristics obviously have been obfuscated. And the argument, which I don't buy, is that you can't reconstruct the original email from this. Anyway, also tested with.
It's a little crypto problem.
I think I talked to a crypto guy at Waterloo, and he said, well, this would be a good first assignment for my graduate course. Anyway, so this is sort of the competition, and this is where the previous published results basically reside. So here's some results from Trek. Now, as I mentioned, we did soft and hard, and I know this is too busy for you to see anything. But this is an ROC curve on a funny scale and truncated. The scale is the logit scale, the same one you love, and if you're into logistic regression. And you see it spans about 4 orders of magnitude of performance here. But basically, this says 0.1%, 1 in 1,000 legitimate emails are misclassified, and let's look at the best one. That's about 2% of spam is misclassified at this rate. Now, again, if you're really paranoid, you say, I couldn't stand even 1 in 1,000 email misclassified. But these 1 in 1,000 email are hard email. They're not email from, Sue to me talking about my talk that I'm about to have. They're stuff that was really borderline or was weird. Maybe it was my guy from Bangladesh. But at least there's some identifiable characteristic about it. If 1 in 1,000 messages from my department chair to me were dropped, I would regard that as unacceptable. But I may find this acceptable. But what I really want to do is I don't want to argue about it. If you want to set the bar here, fine, set the bar here. 1 in 10,000. Then if you pick one of these filters, you can still eliminate 90% of your spam. So on these curves, ROC area is probably the best agnostic single statistic that you can have, which is the area under this curve if you replot it on a linear scale from 0 to 1 on each axis. And a good spam filter will be about 0.999, maybe 4 nines out of a possible 1 in ROC area. That's a little bit annoying, so it's easier to look at the area above the curve. And not only that, the area above the curve is still 0.0001 or whatever, so area above the curve as a percentage is the main summary statistic that we'll use. Before I move on, let me just talk about a couple of these filters. The top one, IJS Spam 2, is Joseph Stephan Institute. It was a filter by Andrei Bratko, who spoke here in November, immediately after Trek. And his filter was arguably the best filter. It used prediction by partial matching, which is a data compression technique. And it used that to model the spam. And I'll talk more about that in a minute, because what I'm doing is very closely related and inspired by Bratko's work. Yes?
How big are the error bars here? How big are these data sets?
The error bar depends on where you are in this curve. I have some error bars later on. If you'll allow me, do you want me to flip forward?
The
the collections, The biggest Trek collection, the public one, is 92,000 messages, about 40,000 Hammond, 50,000 spam. So 1 in 1,000 means you're missing 40. 1 in 10,000 means you're not missing very many at all, and you get, very flaky.
Any inference in 1,000?
Yeah, so certainly the difference between this curve and this curve is not significant. The difference between this curve and this curve probably is. And we do in general have confidence intervals for the tables of numbers that we have later. So anyway, so that's that. The next one, Laird-Breyer, that's actually a version of Debacle, which is a fairly pure but well-founded Bayesian filter. I mean, it really is a Bayesian filter. It's not Bayesian in the open source sense, which means sort of anything that counts things. CRM is the CRM 114. CRM 114, by the way, is a scrambler that is used on the plane in Dr. Strangelove. But anyway, that pretty well tells you everything you need to know about this filter and its author. But it's another one of these open source Bayesian filters, and with a very charismatic author, and it's very commonly used, in fact.
I'll mention one of the co-authors is
Oh, really? Okay. Oh, yeah, that's right. You hired him. Yeah. Anyway, okay. So, 6. I mean, you estimate the likelihood, conditional on it being this and the likelihood conditioning on that, and combine them with some probabilistically sensible way, rather than add up some dimensionally inconsistent set of numbers. And maybe I'm just wrong, but Graham's essay, A Plan for Spam, gives a formula that he calls Bayesian, and I don't see how it's Bayesian. But
so by the popular view of Bayesian is counting.
Bayesian is a synonym for.
And your view is counting with you.
Right. Yeah. Exactly. I mean, of course, the theory of naive Bayes is wrong anyway. So Anyway. 621 is actually Richard Siegel from IBM, T.J. Watson, and it's based on a thing that he calls smarter Bayes, which I don't know the details of, but it involves Bayes, and it's also stacked with another filter that does some path analysis of the incoming servers, the IP addresses of the incoming servers that handled the mail. And the interesting thing is that the thing that looked at the incoming servers was pretty lame by itself, but it actually did boost the Bayesian classification a bit. Bogle filter, standard, open source, Graham slash Robinson derived spam filter. I actually have used that in all the other tests as well. It wasn't the top one here, but it was actually the top one for which the actual configuration used at Trek is publicly available. And it actually performed well on other data sets, and it was actually a very, very strong competitor. Spam Assassin, only the Bayes component did pretty well, particularly out here in the low false positives in. And Spam Probe, and these are all basically, there are none of the standard machine learning techniques, nearest neighbor or support vector machine or logistic regression are represented in any of these filters. They weren't submitted, and I didn't know any easy way to adapt them. So
But it's not because this is online.
this is an online, yeah.
Most of the standard things are not typically run online. So you talk to me offline for the stuff that I've been doing recently.
There's a slide on here. So Joshua read my abstract, and he says, that's complete garbage. I'm going to write a spam filter that trounces all of these things. And he sent me one, and it was actually very good. It was extremely good. And it actually beat Bratko's filter on this thing, but it didn't beat mine. Yeah. Well, that's the challenge is a good thing. This doesn't really say much. We did force the filters to make a hard classification, but really the only takeaway message from this is it's really hard to compare the first and the second filter here. Bogo filter was great at not having false positives. It only had 3 in this of 40,000 messages, and this is online. This is cold standing start classification performance. It only misclassified 3 legitimate email messages, but it misclassified 10% of all the spam. But hey, it got rid of 90% of the spam. But then IJS Spam 2, which got the best ROC numbers, it obviously that wasn't its objective. It wasn't so incented, and it misclassified 0.23% of all the good email. Now you can, by just turning a crank, adjust. You can arbitrarily switch between these two things. One way we did of trying to come up with a composite measure here is, rather than accuracy, and I don't want to get into bashing accuracy too much, but summing the misclassification absolute misclassification numbers and dividing by the number of messages doesn't tell you very much. This, I argue, tells you a little bit more, but it's still, trying to approximate a 2-dimensional quantity with a 1-dimensional measure. So you transform everything into logit space, like the previous graph. Then you average them. Then you transform them back. And this gives you a kind of an average, which at least rewards the improvement from 0.1 to 0.01 the same as it rewards the improvement from 10 to 1, or for that matter, from 99 to 99.9. It's completely symmetric, and it rewards more or less. It rewards fixed factors in the odds of classification with roughly the same amount. So by that measure, Bogo filter actually won, and Bratko's. And then you average them, and then you take the inverse. Sorry?
Did you invent that, by the way?
I believe I did, though I can't.
Was it the normalized version of that, John Sweat's, where you take the transfer?
If you do the standard normal, that's Sweats, but from signal detection theory. But that's actually a little. There you assume you have to make some assumption about what the variance is in order to use the D measure, right? Because officially the D measure is the Z score of the difference between the scores. Oh, sorry, Z transform. I forgot what country I was in.
And you go look at the ROC curves, you'll see it lines up surprisingly well. And I actually, because it's so hard to get single numbers, I actually think that just inventing the Lamb percent is...
Lamb percent is a 45-degree angle on this graph.
And
So, these tend to be very straight for some reason. And a 45-degree angle, and don't forget this graph is not square, but, if it were square, it would be square.
anyway, and so I actually think that invention, right, because comparing these things and always having 2 numbers is so painful, and ROC curves are relatively rare, and a good single number for comparing these things is actually a valuable contribution.
Thank you. And here are the ROC numbers. So here are 3 competing summary numbers that you might use. This is the ROC percent that I mentioned. This is just arbitrarily fixing the x-axis. What is it? At 0.1%, 1 in 1,000 false positives, in what kind of false negative rate you get, and this is the Lamb. So these aren't exactly the same ranking, but actually, the single-digit numbers are the single-digit numbers, and the double digits are the double digits, and there aren't really all that many inversions here. Bogo filter 1 here. So I hesitate to say which of these is best. I mean, and the point about confidence intervals is well taken. Probably the confidence interval, probably there is no significant difference among the top 6 here anyway. Well, maybe there is.
Well, I mean, if things had many parts per 1,000, and we have 1,000, then it's pretty tough.
It's not quite that. If I have 10 errors and I have 20 errors, I mean, you can do exact binomial confidence intervals, and you can. So it's more the factor. Well, it's the sample size, yes, but a factor of 2 difference, even at quite low rates, is still.
Right, but the question then is what's the error judgment?
And I have lots more slides, but not here, on judgment errors. The thing you have to make really sure with judgment errors is if you're making judgment errors, they're not biased. Because just a few judgment, like 3, like Bogo filter only makes 3 errors out of 40,000. if you accidentally let 10 spams through and they were labeled ham in there, the BOGO filter score would all of a sudden go up to 10 errors, which would really suck. So one of the things we had to do is look at the disagreement between the gold standard and what the filters said pretty carefully and make sure that the filters weren't getting screwed by bias judging. And user feedback, users underreport errors. So if you have a filter and you use user-reported errors to measure the efficacy of your own filter, it's basically meaningless. It's certainly meaningless if you then use that feedback to build a corpus that you use to test a competing filter. So this is Bratko's technique, prediction by partial matching. It's a data compression model, and it's quite simple. I mean, at least it's conceptually quite simple. Essentially, you take a window of characters, and you count the number of times the string of characters in that window has occurred, and then you want to predict the upcoming character. And you do that by just taking a window that's one longer and counting the number of times the character you're interested in predicting has occurred. Of course, all of this is necessarily a subset of this. So, and is a first-order approximation to the probability that the next thing is going to be an E, or the next thing is going to be a big E, or whatever. You can build a suffix tree on the reversed text in order to count these things reasonably efficiently. And so what happens is we're going to compute the likelihood, which means we're going to take the probability conditional on, if we guess that this is spam, what's the probability of this being an E, a little e, or a big E? And if we assume it's non-spam, what's the probability? So we build two different models, and let's look what the two different models predict. In the spam model, this occurred 509 times. And 0 times it was followed by a little e, and 509 times it was followed by a big E. So we just divide those and get a probability estimate, right? Probability is 1 that it's a big E, and the probability is 0 that it's a little e. Well, of course, that's a lie. Probability is not 1. The probability is somewhat large. And similarly, if we look at the other model, the one for ham, this has occurred once and exactly one time. It was a little e, and exactly never it was a big E. So, same thing, probability 1. Well, obviously the probability 1 with which we predict a little e for the ham is a smaller value of 1 than the probability with which we predict a big E for the spam. And this is an unsolvable problem, which value of 1 is bigger than the other value of 1. But what we do is we then put in some kind of smoothing or some kind of back-off strategy. And the back-off strategy in PPM is said, well, we'll repeat it all with one shorter context. And we'll keep using shorter and shorter context until we get enough. Now, we're not going to throw away this estimate. We'll make it 50% this estimate. But, once you average a 1 with some other estimates that are not 1, then you get, an estimate which is not 1, which is a desirable thing. So if you're compressing, what you do is you just whip out your optimal code and you get something that's minus log 2 of this probability bits long. Or if you want to look at this as a likelihood, the length of what you came up with is just a log likelihood. Well, negative log whatever. It's related to the likelihood that this feature will occur under the assumption that it's ham or the assumption that it's spam. So then you can take the difference of those and you get a likelihood ratio. And typically what you do is you normalize this over the length of the message. So it's actually the likelihood per character, which is a little bit strange, but that's just because these things aren't really independent, and it doesn't, you're not really getting more and more and more confident. The more, when you see the D here, the little d here, or the big D here, it doesn't really teach you anything, even though a naive combination of this would do that. So that works well. So the other thing that Bratko did, which gave quite a substantial improvement, is he adapted. Typically, people have said, well, you build this model statically and you freeze it, and then you use it to do all these predictions. As a data compression algorithm, what this does is immediately after it learns the answer, it updates the data structure. So the next time it sees this context, there'll be 510 spams or whatever. Or in the ham case, the next time it sees the context, it'll say, I've seen this once in a ham and once in a spam. So the next time it sees it, it won't further amplify it. So it will only have registered that that's an anomaly once. Anyway, Bradco and I have written a paper on that we've submitted for publication, and certainly this is basically Bradco's work. My work is inspired by Bradco. I dusted off a data compression method that I invented in 1985 or something like that. I mean, it's called DMC. It's almost as good as PPM. In some specific cases, it's better than PPM. With heterogeneous data, like if you compress .exe files or something, I tend to be better than PPM. But for garden variety text, or the things that most people want to zip, PPM is a little bit better than mine. But it's competitive. Sorry?
That was the previous.
Oh, sorry. PPM is a standard adaptive data compression routine. It's been the standard to beat for years. I mean, bzip 2 might be slightly better, but it would be right on there. And if you search find any data compression fact, it'll be one of the first things that's listed. So prediction by partial matching. Anyway, so DMC is a little bit different. It doesn't start with a big context and then back off when it doesn't have enough information. Yes? Dynamic Markov. And there's some ambiguity here. It's either dynamic Markov coding, which is what I think I said in the title, or dynamic Markov compression. And since we're not actually doing any compression, I chose the coding alias. So what it is, it's just a finite state machine on the bit string. It doesn't even concern itself with bytes. It concerns itself with bits. And so if you have a transition, for every transition, there's a frequency, which is labeled X. X. Yeah, that letter. Which is labeled F here. So basically, if you're here, you can estimate the probability that the next thing will be a 1 by taking the or the odds anyway, by taking the ratio of the number of times it's been 12 or it's been 1 before to the number of times it was 0 before. So in that sense, the idea is the same as with PPM, except we're predicting bits, and we're getting these counts of previous occurrences in a completely different way. So we start off with a very simple model, something like this, maybe 1 state or 8 states or some small number of states. And then what happens is whenever we follow an edge, as in this red edge, this says we were at A, we saw 1, we went to B. And what we do is we grow this finite state machine. And the way we do it, we grow it, is by a process known as cloning. And what cloning does is it takes the target of this edge, and it creates a copy of it. And what it does is, first of all, there's a cloning threshold. You'll only clone this state if you visit this edge more than some number of times. Currently, it's set up if you visit it twice on the second visit, you'll clone. So it's pretty active. And it will also only clone it if there are transitions into it from other states that exceed some different threshold. Now, there should be an arrow here from other states, but we don't have back pointers, so how do we know? Well, we've got these counts. The total outgoing count here is 16. The incoming count here is 4. So we know there must be, what's 16 minus 4? There must be 12 other, there must be edges with a total in count of 12. So that's big enough. So this is now a candidate for cloning. So what we do is we copy this. All we do is we split the proportion of the edges between the old and the new state in proportion to how many times they visited from this edge and how many times they visited from all other edges. The all other edge proportion stays with the original, and the new proportion is computed. And then the very last thing we do, this is adaptive, so we increment the frequency on the edge that we actually took. So we clone first, and then we follow the edge and increment it. All right, so this has the the sort of effect as the next time you come here, you get one bit more context. And the next time you come here, you get another bit of context. And the reason for the thresholds is you don't want to be growing a whole, essentially, decision tree if only one path is being taken. So you only actually are cloning when you have two active predecessors. So that prevents you having gratuitous exponential growth of the size of this model. It only grows linearly with the amount of input. It grows fast linearly with the amount of input, but it's still linear. Okay, so you do that, and then all the other stuff about computing the log likelihood and stuff is the same. And also, once again, you can turn off cloning and incrementing if you want a static version. But if you leave the cloning and the incrementing of the counts turned on while you're doing the classification, you actually get better results. Okay, so the first thing I wanted to do, because this is not, yeah, this is almost the way I did it. So Bradco stuff worked great. I did DMC, it worked great. I tried it on a different one of the Trek Corpora. I didn't try it on the one I'm showing today. I tried it on one called Mr. X, and it seemed to work really well. I did almost no tuning. I basically took, there's a public version of DMC on the web that is kind of free for so long as you don't sell it or something. And I basically took that and did an evening's worth of adaptation and took all the cloning parameters and everything straight out of the box. I truncated, I only used the first 2,500 bytes of each email message. I just threw the rest away. I didn't do any MIME decoding or anything like that. And it worked pretty well on Mr. X. And then I went back. And this is something that's been bothering me for a long time in the Trek context, not just in the context of my own stuff, is reconciling results on these tenfold cross-validated public corpora and the Trek results or any other results. Because, referees are very fond of saying, support vector machines are known to be the best possible supervised learning techniques, and you haven't proved that they're inferior, so, we don't want to consider this result. So obviously Trek doesn't prove anything, and neither do I prove anything, because of course I can't prove a negative result because anything I do with support vector machines is limited. It's to start with, it's cigarette company research, and second, it's limited by my skill and ingenuity and everything. As Joshua proves by coming up with a logistic regression implementation that's much better than mine. That said, so we went and we said, well, let's play on their playing field. And I actually was very surprised by these results because I expected them to be a bit worse. I thought we might be competitive with the batch results. But in fact, we trounced them. And this is just straight out of the box on the Linkspan corpus. The red line is me and the green line is Bradco. So Bradco wins here. Yes?
This is on bits, not characters.
DMC works on bits. PPM works on characters. So
It seems kind of weird to work on bits.
In fact, there's no difference because if you predict a bit, if you've got the probability distribution for characters, you can take any binary encoding you want for the character, and then you compute the conditional probabilities of the decision tree, of the bits, which form a decision tree to get to the character. It doesn't matter.
Doesn't it take longer to learn, the AU relationship?
Does it take longer to learn? Well, you can turn down the threshold parameters, and then it'll learn real fast. Your intuition is well taken, but empirical results are, in fact, that the DMC learns much faster, and in particular, right out of the starting blocks, learns faster. It starts to compress after the first 3 bytes of the message. Whereas PPM, wants all these big string contexts and even getting a sensible probability distribution of an alphabet of 60 characters is going to take you hundreds of characters, not tens of characters. Yes?
Your starting tree, your starting state, you've got 8 states. So in some ways you are right.
I can put some bias toward bytes by having a starting. Remember I mentioned you can start with just one state. If you start with a state that has an inherent cycle length of 8, then you are implicitly, basically, you're taking the character boundaries as a ninth. It's like having a stop bit on everything. So that in that sense, it is a little bit byte oriented. That gives you a measurable improvement. It's not a slam. I don't know. I'd say 10% better compression, but then what does 10% better compression mean? On text, DMC, with the more complicated starting model, probably compresses to 2 bits per character, whereas if you don't do that, you might get 2.2 bits per character, 2.3, something like that. Anyway, basically, over all possible threshold values, both of these basically are better than the published results. Now, there's a couple I should mention here. This green triangle up here, P suffix trees, this is actually work that was done concurrently with ours and is currently a technical report, I think, submitted for publication, and I've corresponded with the author. But hey, it's based on suffix trees. It's based on suffix trees that look at the past contact. Oh, gee. So it's actually very similar to PPM, except it takes the suffix tree, and then it has a number of ad hoc ways of combining evidence from the suffix tree. But it certainly is farming the same information that PPM is.
And where is it on the phone?
Oh, that's this one green. Because you see, if you use a hard classifier, you only get 1 point here. If you use a hard classifier with a couple of threshold settings, then you are entitled to several points. So, for example, this is Hidalgo. I don't even remember exactly which technique this was he used. I think it was just Bayesian with I'm sorry, it is referenced in the paper that I'll reference later, but I've forgotten the details of the method. But he gets 2 points, for example. And he's pretty competitive. Not quite there. I mean, there's a big difference between 0 misclassifications and 10 there. And here is pretty good. But again, it's from 20 to 40 or whatever, something like that. Anyway, so I think this demonstrates this at least competitive against these previous results. And it's K nearest neighbor and Bayes and stacking and so on are there. SVM. There is an SVM point here. Should be. Oh, maybe on my next graph there is. This SVM, this is my reference implementation of SVM. It's basically, I just used SVM Lite and did a very simple translation into binary feature vectors. And I did the same thing and applied an off-the-shelf logistic regression technique. And so they're competitive. They're certainly competitive with the published results, but they're not, substantially better. The Josh number? Oh, you want to see the Josh number? You really? You don't want Josh. Josh asked me not to show you the result on his result on the Link-Spam corpus because it was just too good. He wants to save it. I have not done a full test with Josh. Josh read my abstract for this talk, and we talked on the phone, and he sent me this thing. So I ran his test on the online Trek corpus, and actually I ran it on the Mr. X corpus as well, and it looked really good on those, but I didn't have time to do all the tenfold.
You ran on this, but even it was horrible. That's why I asked you not to share it.
Oh, I'm sorry. You're right. I ran it on this, but I didn't do the full tenfold on anything else, and so I haven't done a full test on. But I don't.
On this corpus, but this corpus is particularly.
But I don't think I don't think that's any shame. And if I speed up a bit, I assured Sue I'd be done by 1/2 but I guess I lied. If I speed up again, I'll show you that more adaptive methods often suck on tenfold evaluation because a lot of the information that they use is being obfuscated. Anyway, the next one is PU1, and this. Of course it doesn't, but it is the de facto standard. And you can't just write a paper that says the de facto standard makes no sense, and here's my own evaluation. Have you tried doing this recently? Anyway. Okay, so here's the PU1 corpus. Recall it's like Link-Spam, only the good news is it's real email. The bad news is it's tiny. It's only 1,000 messages or something like that. And the other bad news is there's this obfuscation. Everything's translated into strings of decimal digits, which are arbitrary. So, what do we do? Well, now SVM, I mean, you really can't say there's any difference between SVM, among SVM, logistic, DMC, PPM. I can cheat a bit. This uses the actual decimal numbers in ASCII as they are in the PU corpus. If I take those numbers and convert them into 16-bit binary numbers and run DMC on it, DMC actually does a bit better. And I don't think it's really cheating, because I'm not adding any information to the to the corpus. I'm just transforming it a bit in a way that DMC likes. Just because DMC, if you use a ASCII decimal representation, you're getting to start with variable length tokens, which DMC doesn't appreciate. And also, if it's exactly a 16-bit, DMC knows that it's 2 bytes long, and it can see exactly where the boundaries between tokens are, and they're shorter. So, it gets to clone and adapt faster. So for the same number of bits of context, it can make a better prediction because that representation is shorter. So that said, so the confidence intervals on all these are like something huge. Nevertheless, I'd say, certainly I don't see any, prior results that are demonstrably above there. If you want numbers, here's some numbers. Finally, you get some confidence intervals, which are done with a bootstrap on the difference of the logit transformed numbers, which seems to be pretty normal and works nicely and agrees with SPSS and some other packages. So, area under the curve, Bogle filter. Well, that's interesting. I thought Bogle filter was bad. Well, I'm not showing you the whole curve here. This is actually a very small part of the curve. Only, I don't know, what's 30 divided by 610? And this is smaller, but I guess Bogle filter comes into its own in the extreme parts to get a better area of the curve. I'll show you some more examples of that in a little bit. But I should also mention, for Bogle filter, I did have to transform the input for Bogle filter. If I used the decimal ASCII representation, Bogle filter sucked. It was basically no better than random. But if I translated, 0 to A and 1 to B, 2 to C, and so on and so forth, then Bogle filter gave these numbers. So Bogle filter definitely treats, strings of digits differently from strings of alphabetic symbols. So here are some numbers. Again, the confidence intervals are huge. So I'm not really sure, what I can say about those numbers, other than the fact that you can do a meta-analysis and you can say, you run this on 10 corpora and the ranking is similar. You can start to infer something independent of the significance of any individual test. So by this measure, they seem these are worse on Lingspam. But Bogle filter, like I say, is competitive with the rest, and DMC is a little, seems to go a little awry at the fringes. Okay, so here's the real test. This is a track corpus online. This is the same one that Bratko won. So here, here's Bratko in the green. So that's PPM in the green. That's DMC in the red. Bogle filter is pretty good, only it kind of falls off there, and that hurts it a lot in the final area under the curve score. And here are my implementations of logistic regression and support vector machine. And again, I want to say, I've scaled this graph so that these look really bad. But actually, these would be perfectly good entries at track. They're not, disgusting. What do these do? For the first 1,000 messages, I train on all the messages up to the one to be classified. I use that as a test set of size 1 and increase. Beyond that, it gets a little bit slow, so I use larger and larger batches. And in the limit, I use 10,000 messages as a training set and 500 messages as a test set, just with a sliding window going through the whole corpus. Here's what happens if you decompose the track corpus into splits and do 10-fold cross-validation. That is, you ignore the order. Well, you can't quite ignore the order, because what do you do with the adaptive methods? The adaptive methods, like DMC, needs an order. It's biased towards what it's seen most recently. So you pick some arbitrary order. In this case, I picked random order for training DMC. And in fact, you see what happens relative to the other graph is DMC is actually staying about the same. It's actually slightly worse. Whereas all the other filters say, wow, this is great. I love 10-fold validation, and give results that are ordered of magnitude better. But PPM is by far at the top of the heap, and Bogle filter is second. And then you get your, then logistic and SVM aren't nearly so embarrassed in this test. But as Sue says, it's What does this test say? I'm not sure. It says that ppm works well. Here's what happens if you do a more sensible batch-oriented evaluation. So you split the you still split the corpus 90-10, but the 90 is the first 90% of the corpus, and the 10 is the last 10% in chronological order. So when you do that, well, then you get interesting curves that cross all over the place. And in fact, the red DMC curve actually has the highest area here, because it actually hits 0 at that point, and it hits 0 at that point. So, you know, it can do a no error classification. Whereas the rest, in the kind of middle mushy area, are above, but they have tails that go on forever that hurt them. So, you know, I won't say any great conclusion about this. So this is what happens with DMC when DMC adapts on the test set, adapts on the training set, and then is frozen, and without any adaptation. It still does the pseudo-adaptation, but without any training, it evaluates the rest of the corpus. So after classifying every message, its state is reset to what it was immediately after the training data. So there you go. So then there's another test which says, okay, I'll still do this split, and I'll still have a training and test set, but I'll allow the adaptive filters to adapt. I'll process the test set in order. And as you can see, well, all the filters do better, but in particular, DMC and ppm do way, way better. These are on the same scale. Same messages, same scale. Way, way better. And once again, DMC still has the property that it hits the X and the Y zero axes with appropriate choice of parameter.
Why do the non-adaptive methods change?
The non-adapt. Oh, I'm sorry. This is using the adaptive methods. So this is this is my adaptive hack of logistic and my adaptive hack of SVM. So let me go back. So yeah. So maybe these are not as comparable as you'd think. These are SVM and logistic with their batch training mode. And this is with their adaptive training mode and with their adaptive in test mode. Okay, so these were the ones that were really bad on the corpus. But it turns out that if you look at the actual numbers, that I mean I'm overwhelming you with numbers here, but see ppm goes from an area under the curve of 017 to 006 from online to batch, or sorry from online to batch. This is with the overall numbers, whereas DMC gets slightly worse. And the LR and SVM, this is my adaptive version and this is the batch version. The batch version is much better. But in terms of the I'm missing. Okay, I'm sorry. The columns that I want to talk about are right here. So this is the chronological split. So what happens is, in batch mode, LR and SVM, you know, are substantially worse than the DMC and ppm. And in adaptive mode, they're still worse, but they improve a lot. So even these really bad adaptive adaptations of these methods perform better on the actual chronological processing of the test set than do their batch equivalents.
And the order of these messages is just the date?
Chronological order, as far as we could do, it was chronological order at which they were delivered to the final trusted server.
What's the time span of number one? This seems to be indicating that the nature of spam.
Well, in this corpus, the nature of spam is changing a lot, and the nature of the non-spam is changing. This is the Enron corpus. This is a corpus that was, you know, going through huge transformations and was in free fall and went into receivership, and so on and so forth. But the spam is also changing. So it's certainly an open question to analyze. I don't think it's all that atypical. Maybe this varies more. The general results still apply to the other corpora we have, But what I haven't had a chance to do yet is do the random order and the cross-validation on the other corpora just to see how much that hurts.
And what time span do you have in chronological order?
These would be over about a year.
So it says that updating your filters every couple of weeks is probably important.
It might be. That hadn't been my kind of intuition. And maybe every couple of weeks is not good enough. We don't know how close the locality is really that this is harnessing. Actually, it's pretty close because, I mean, certainly doing the chronological split. Oh, I got to show you something. Here, look at this number. This is what happens if you process all the, if you train DMC on all the messages in chronological order except with the one test set removed. So it was removed from its hole. There's a hole where it should be in the chronological. Well, it's not a chronologically contiguous, but you remove all the test set messages and then process the training set in chronological order, and then you try and process the test set. DMC gets killed. It gets absolutely killed. So training for the whole year in order and then trying to evaluate a random subset of that year absolutely trashes DMC on this course. It doesn't hurt. It hurts PPM, but not as much. But then if you let it adapt, it still hurt, but the hurt is mitigated by about a factor of 10. You've trained it on something in exactly the wrong order, but you've given it incremental feedback in this thing that obviously is not what it expected. It learns pretty quickly. I should do all that. But doing these tenfold things on 92,000 messages takes a little while. and then people from Microsoft say, well, test mine, and
I'll just say that on Hotmail data, we know that frequent updates, like ideally once a day or two, makes no sense.
okay.
As you use it longer and longer and longer, does it adapt slower and slower?
No, it grows and grows and grows. So what you have to do is you can crank the threshold parameters up, but actually it works better just to throw away the model, retrain it on, keep the last 1,000 messages around and do that. If you give it, you would need several gigabytes of data to do the whole corpus without having to throw away the model. So it grows, there's research to be done in is there a smaller data structure that will represent the same finite state machine. And clearly some of those states are not visited as often. I have a very interesting systems-oriented thing. I ran this with a 2 gigabyte buffer on a machine that had 2 gigabytes, and it ran just fine on the chronological corpus. But when I did it on the random stuff, the system thrashed like crazy, and I had to, and it took 10 times longer to run. And that must be locality within the finite state machine. Tokenization hurts. Obfuscation hurts more. That's the red is the original. This is PPM on the batch. Tokenization hurts. Obfuscation hurts more, but it's still more than competitive with the batch-oriented systems. You don't care about those numbers. Here's what you really care about. Goodman's gradient descent. That's the blue. So it is a substantial improvement over my effort to make logistic regression work. A little bit of that might be feature engineering. A little bit of it might be other magic. I'm not sure. No reason to believe that Goodman has milked all the, used all the tools and tweaks that he has. But then, and again, yeah, I don't expect you to believe me, but the DMC is pretty well straight out of the box too. Are these the best? Nope. If you take all the 53 filters that were submitted to Trek, stack their results, that purple line is what you get. You combine their results. So the easiest way to stack them is they all say spam or ham. You just add up the number of spam votes. and you use that as a score between 0 and 53. You can be a little bit smarter by by taking their score and fitting a model to try and figure out what the probability is based on the score, and that's actually what this purple line is. But the just counting the votes is already substantially above the red. Yes?
So, but given that they're using very different techniques, like Goodman-Cormack combination, how do you have any idea?
I have not done that. The only data point I have on this uses logistic regression to actually combine to do the stacking. Logistic regression drops out the filters that don't get significant coefficients. Bratko's method did not get a significant coefficient. So Bratko's method is actually not making any contribution to that purple line. And neither is my method because it was not tested at Trek. So there's gold in them. I can't say this. All right. I have a couple of papers that describe the DMC filtering and the stacking. You have to ask Joshua about his technique. Those papers also reference other papers and technical reports, and they're roots for anything you might want to know about this, I think. We need to test on different corpora. How much do they vary temporally? The other thing is, if you have 1 billion messages a day coming through, maybe you can fit the last 5 seconds worth of messages in your buffer. Is that enough for you to be able to predict the next 5 seconds? Or you need some kind of adaptive but more global than that? I don't know. I don't have any method to evaluate that. You do. Well, you still have difficulty, as Joshua pointed out to me, because you don't have any gold standard judgments for those million messages that arrived in the last 5 seconds. So I don't know how you know whether you're doing a good job. I suppose, anyway, I don't know. So there are practical issues. RAM, in a personal environment, you would have to have some kind of paging or some way of writing the state to a non-volatile, non-volatile memory, because you probably don't want to dedicate 2 gigs of RAM or 1 gig of RAM or whatever you need to this process, so the more thought would be needed there. Server implementation, the big question is just sampling these 5,000 users and having a common bag of RAM for them sufficient? If it is, then this basically just drops in. If it isn't, then you have to, you're not training on exactly the same thing that you're testing on, and it might get a little bit more complicated, and you'd have to decide. There are many things that are not known. And then the ML methods. I hope this is a challenge too, because the people that explain why SVMs work and why logistic regression works and things aren't completely crazy. And so maybe in this context we can engage that community, and they can say, well, this is how you should be making use of what you've learned from this, and then applying it using the better ML techniques in order to get even better spam filtering. I'm done. No more arguments?
Practical stuff would be one of the personal implementation that we run into also is that people want to make sure that things like ML is deleted is really deleted, because there are nasty, right? Those Enron people, right? We probably wish they deleted some of the ML permanently. We get into a lot of nasty issues with.
Yeah, well, when they turn the the microphone off, then I can tell you some anecdotes about information in the corpus that they might wish they had deleted. But in fact, there's even with this supposedly public information, there's still strong ethical reasons why you have to try to avoid spilling too much of what's in it. So we have you've read our usage agreement, and somebody malicious could obviously break it and mine it, but then they can mine it from other sources. I don't think there's any value add in our corpus over what they can get from somewhere else.
So the point I was just trying to make is that personal implementations have a lot of.
Yes.
There's actually a lot of issues in terms of saving this stuff.
You're certainly saving it on a server, saving it on a laptop.
You're saving it on a laptop because subject to legal search of the blog. The
yeah.
the corporate
yeah.
environment, people want to know that when they leave their mail.
Yep. Yep. Well, that might be an argument for adaptive, though, because I have reason to believe that you can use a fairly short time window. I mean, I don't think people they want their email to disappear forever within a reasonable time period, like before they anticipate any lawsuit. So if you're not anticipating any lawsuit in the next month, you might think a month window was usable. Yes.
Try to use it with a machine built by DMC. When you infer something about it.
Yeah, you can. We inferred, for example, one time when we were first testing DMC, we thought we'd try it on random bit strings. So we used the Unix random function, the last bit of that, and we ran it and it compressed it down to 0. And we found it had a cycle, depending on what seed you started with, it had cycles in it, that were as short as 2,000 bits, sometimes 30,000 bits, things like that. So, I mean, that's not quite the same as discovering, your secrets, but yes, you can learn a lot about the source from looking at the model. Yeah. You can freeze it. You can generate, email. No, it's not random text. This looks like a brain damaged version of Charlie wrote it.
I don't think it's admissible as evidence.
No, but if I just want an intuition.
Randomly generated.
No. If I looked at text randomly generated from this for your email, I would get a pretty good idea of what your interests were and who you corresponded with and what they said. It's like these programs that generate porn or generate papers for submission.
Expert on one side and I could be an expert on the other.
It doesn't matter. I mean, if I were doing that in the legal sense, I would say that's enough for probable cause, right? This subject matter looks like something that I can take to a judge to get a warrant to search your computer.
I was surprised. Just you essentially got one corpus that is real mail. Right?
No, we have 4, but 3 of them are private.
Okay. Are they comparable size?
One of them, the private ones, one of them is 50,000 messages, one of them is 170,000 messages, and the other is 7,000 messages. There's also the spam assessment corpus, which is public and not great, but really all the results are generally, they agree as well as you would expect, given the confidence intervals and other sources of heterogeneity. There's certainly a need for more, but it's really hard to get standardized, realistic corpora. So yeah, all of this should be taken with a grain of salt. That, I mean, the overall performance on the Trek stuff is reproducible on the other corpora, but the tenfold stuff and the chronological split stuff I have to this date only done on the Trek corpus.
Do you actually write your will so that since the mail sent to you, I think is copyright, you own the mail sent to you, is that right? You could actually put it in. You could put it out, like will it to the public domain as the.
Is mail sent to you? I don't think so.
It's horrible. Nobody knows what the deal is. Right? This gets we run it.
You want me to will my mail to? Sure, I could do that.
Yeah, because you're the Mr. Expert.
I think that Bradco made the mistake of writing in one of those papers that the corpus was collected from the mailbox of one of the authors or something like that. But that was just a typo. Okay.